Thank you so much for talking to us, Dr. Andrews. And without further ado, the floor is yours. Thank you.
Thank you very much. I'll turn my screen on here in just a second, but thank you for the invitation. And I also want to congratulate Irene on a great talk a few minutes ago, and then also on the award. This is wonderful. So let's see, a quick little note. Some of the research stuff there that I do, like the crystal, you're a mineralogical society, and so if we think about minerals that are growing in a magma, like let's say thinking about why does an obsidian have basically no crystals in it, at least if it's the good weapons grade stuff, whereas a basalt lava is chock full of crystals. And we can think about that. It all has to do with the nucleation and growth rate. So how fast can little crystals start to form, and then how fast can we grow them? And it turns out that making little blobs of magma in the lab, we can start to answer that question. But I think tonight, if I understand the program correctly, we are hoping to talk about something different. Let's see if this works. So I want to thank you for let's see, first, can everyone see the screen? Thumbs up or something if you can see the screen?
Yes, I sure can.
Great. Thank you very much. So tonight I'll be talking about patterns in global volcanic activity, which is a little bit of a catch-all title. My PhD advisor would probably joke that you can discuss anything and nothing with a title like that. So we're going to try and hopefully go for a little bit of everything, and then a focus on some Kilauea activity. And for the folks wondering what this picture is of, this is a 30-second exposure of Santiaguito volcano in Guatemala about 10 years ago, I guess almost exactly 10 years ago, a 30-second exposure of an explosion happening. And so you can see incandescent rocks flying through the air. The field of view is about 3 football fields across there. So it's throwing big rocks quite a ways up in the air. So our talk tonight, this works. Our talk tonight is going to have two parts. The first part will hopefully take about maybe 10 minutes, and I want to talk a bit about the Global Volcanism Program and a resource that hopefully all of you have used in the past and will use again, and some new developments and exciting things we have in there. And then we'll cut to I'll do a short overview of the 2018 Kilauea eruption, the one that was in all the news about, I guess, 4.5 years ago, almost 5 years ago. And as I'm doing this, the second part of the talk relies almost entirely on a USGS resource that I want to share with all of you, because they were the folks studying the eruption. They have some fantastic source material out there for all of us. All right, so I just clicked the wrong button. All right, so for a little bit of background about the Global Volcanism Program, if we want to think about how we study volcanoes, or rather the museums are all about collecting stuff. So when we're looking at the volcanoes, they're pretty big. They're bigger things than we could normally collect. For those of you who know, this is the Museum Support Center in Suitland, Maryland, and each of those buildings is these ones in the foreground, that sort of a stack of 4 of them there, is about the size of a football field. And that's where all the Antarctic meteorite collection is. That's where half of the rock and ore collection is. It's a pretty big place, but it's pretty little compared to a volcano. And that is actually a real volcano. It's one of my favorite volcanoes out there, BAM. It's off the northeast coast of Papua New Guinea. It has a particular identification number. It most recently erupted about 63 years ago. So this is volcanoes are too big to collect. So we don't collect the volcanoes. Instead, we collect the data that describe them. And we do that through a relational database. And don't worry too much about what this is showing right here. It's just saying that there's lots of different types of data that go into a volcano or into the database. There's data describing the volcano, like its name. It's a unique identifier. So just like all of us have a driver's license number or a social security number or a passport number, every volcano has an ID number. There's location information, so it's latitude and longitude, names of its subfeatures. So if we're talking about Kilauea, as we will in a few minutes here, Kilauea is a volcano, but it has various other vents and features on it, like the Pu'uo'o cone or Makuapui or other other features that are on that volcano, and we want to keep track of those. We also might have images or reports or samples that are associated with this volcano. And we also have to think about eruption data. So we don't just want to know where is a volcano, we want to know when did its eruptions start and stop, what was happening in those eruptions, and then what was the type of activity? Was there lava flows or explosions or what have you? And so starting in the Global Volcanism Program started in 1968, and starting in 1971 to the present, we've developed a database of volcanoes and eruptions. And so in 1981, this book was how you would access the database. It's 233 pages. There's still a few copies of this floating around. And so it's like a phone book, and you would just look up a volcano and you could see what its history was. And then 13 years later, we released the update of that. So version 2.0 was another book that you can see is about 50% thicker and has more of the same information. The following year, the Global Volcanism Program launched a website that contained almost all of this information as something that you could see on the World Wide Web. You could get on the information superhighway and see what was there. And then in 2010, we published the third version of this, which you can see is again about 50% thicker than the previous version. And this one is the final. There will be no more paper versions, no more book versions of the database ever, because we did a big redesign in 2013, and this now allows people, and that allowed people to download the data. So it used to be if you wanted to get the data, you would have to flip through the book and enter the data by hand or re-enter them or something like that. Now you can just download it, and this is wonderful. In 2016, we started adding additional or made available additional data, including volcano deformation, so how the ground is moving up and down at a volcano. We have that for some volcanoes. And then emissions, so what gases are coming out. Mostly SO2 is what we focus on, but that data is now all in the VOTW database, or the Volcanoes of the World database. Some of these data were displayed then in the E3 app, which is an online, like a video app that at the moment is having some troubles. And then if we look at what the total number is, I checked this yesterday, and as of yesterday, there are 1,328 Holocene active volcanoes that we keep track of. And there's more than 11,000 eruptions that we have kept track of, or that we've documented. So a wealth of information. Now, if you wanted to access this, you can go to our website, volcano.si.edu, and you can see, and we're going to go through a little tour of this website very quickly before we go to Kilauea in a couple minutes. We can see all sorts of different information. We can get reports, the database, different FAQs, all sorts of good stuff. So first off, each volcano's information is available on a profile page. So one of the things that you get to do when you look through our list of volcanoes is you can find favorite volcanoes, or ones that you didn't know were your favorite until you see that, yes, there is a volcano called Penguin Island. And so you can go to Penguin Island and you could click and see what its eruptive history is. You could see that I don't think there's any weekly reports because I don't think it's done anything in a long time, but there's a possibility that it would be there. And every volcano has its own profile page. So this is like, you can think of it like a Facebook page for each volcano, except that we were doing this before Facebook. So really everyone out there that has a Facebook page has a volcano page. All right, now something else that's really exciting are the images and videos that we have. So right here, we're going to see if this works. I'm going to click on our website to try and get to the image collections, because this is something that I think is exciting, and hopefully you will find as well. All right. Move this over here. And do you see a website or not? Cindy, can you tell me if you see a website?
Yes, I
Okay.
did see a page.
Okay, great. I just want to make sure that the screen switching between programs is a scary thing. So if we go to the image galleries, we can see that there are the sorry, something just now if we go to these image collections, we can see that there are different types of galleries. We have hazards and processes, or research, all sorts of things. We can also see particular theme collections. So this is one that I think might be of interest. So we've gone through and we've organized thousands of photos and recaptioned them. And then in this instance here, we've started to put in some that are by particular some folks who've contributed large amounts of photographs, we started to give them their own galleries. So their photos might appear elsewhere, but in this instance here, we could look at things from like Jim Luer, who is one of my predecessors at Smithsonian. And it's entirely possible he spoke to your society at some point, 20 years ago or more. We can see that here's all these amazing photos, and if we look at this one here, we can see here's the photo. In this case here, it's a field trip. We can see this deposit, and we can see the caption right here. And these captions have all been done by scientists at GVP. These images have also all have keywords associated with them. So you can then search through and find these different images that way. So I'm gonna just try and make sure I keep going to my next one. Right, the next thing we could look at in here is we could look at map holdings. And so every volcano has maps associated with it. I think I'm, all right. So we could see map holdings, and in this instance here, we could go to, for example, we could look at Hawaii. We could see different maps that are associated with it, and different. These have all been georeferenced and scanned in. And in this instance here, sorry, this is Penguin Island we're looking at. We have all of these different maps have been scanned in and georeferenced. And so, yes, you can go to Google Earth and you can get fantastic imagery, but sometimes you might want historic imagery. You might want historic maps, and that's something that you can get from our website. We could also look at samples. So in this instance here, if we were to look at Kilauea, on its page, we could click on the tab for samples, and we could see that more than 2,400 samples from Kilauea are in the Smithsonian's rock and ore collection. And you could click on any one of these and then see some information about it. And even find out, with a little bit of work, you find out what work has been done on it in the past by contacting us. So there's a great deal of information here of use. Now, the other thing that's really good in here are the narrative reports. And so we open this up now. We can see that there's two sets of narrative reports. There's the bulletin, which comes out approximately every month and has a detailed structure, or sorry, a detailed report. So for instance, here we see something for Santa Maria. If the website opens up, and we'll see that it's providing a multi-page, see lots of reports from Santa Maria. We can see a description of this, sorry, I need to go to the most recent report. We can see that this most recent report is a long text report, and it has information in this instance, satellite observations. There might be images, there might be descriptions of what's happened at this volcano. So it's providing a detailed picture of what had happened at this volcano. But we could also look at weekly reports. So every volcano has, the Smithsonian USGS for more than 20 years now have partnered on a weekly volcanic activity report. And this comes out every Wednesday, or is published every Wednesday. And we can see in this instance here that for this most recent week, there are about 20 or so volcanoes that have reports. 5 of these have new activity showing up, and the other ones are ongoing eruptions. So we could look at Aira volcano, and we could see a description of this ongoing eruption at Aira and Sakurajima. Now, the other thing that shows up in here are eruption histories. So if we wanted to study, for example, look at Kilauea, we could look at its eruption history, and we could see that Kilauea has been active, but it hasn't always just been erupting lava. It has done other things in its history. So right here, if we were to look at in here, the eruptive episode that ended in 2018, we can see that it has different types of events associated with it, explosions and lava fountains. There were evacuations in 1985, additional evacuations in 2009, that looks right. And there's some additional stuff that's still coming in here. We could also see, if we went back into the 20s, we could see that there were, I chose the right one here, there were explosive eruptions and a partial caldera collapse, or partial collapse of the crater. And on May 18th, 1924, there were fatalities associated with it. So we can see that there are different types of events associated with even a volcano like Kilauea that we think of as being, it just always gushes lava. Turns out it has a lot more complications than that, and we can keep track of that. Now, in the abstract for the talk, I mentioned that, I think I said something like, news reports are always saying that volcanic activity is increasing. And I want to, if you look at a graph like this, that would certainly be the picture you get. And when we turn on the news and a volcano is erupting, there'll be these almost like hyperbolic descriptions of the volcano is erupting more than ever and ever. This is not good. And so if we look at a graph like this, that looks pretty bad. It does look like it's increasing. If you project this out to, say, 50 years in the future, you'd be expecting like 200 volcanoes erupting every year. That's terrifying. That'd be really bad. Turns out that there's more to the story than that. So if we look at this in detail, we see that there are there's dips in the frequency of eruptions that coincide with World Wars I and II, and which should raise some questions. Does anyone think that if there's a big war going on, does that mean that the volcanoes start erupting less? I can't see anyone's faces, but I heard Cindy chuckle. No, the wars are terrible things, but the volcanoes don't care about wars. The volcanoes are doing their own thing. So it turns out that a lot of this is observational bias. So when there's a war going on and you're dodging bullets, you don't report on all the eruptions. And so we see a downtick. When we have satellites observing, starting in the mid 70s or late 70s, and then some additional things that have happened in the last decades, we see that there's an increase in eruptions that are reported and detected. But over the last, if we were to extend this out to the present, instead of stopping at 2015, if we take it out to 2023, we see that this number basically holds steady now. So we think we're probably seeing just about everything that's happening now. And so it really is an observational bias. And this shows up if you start to look at the bigger eruptions. So a VEI2 is something like, it's like what Kilauea was normally doing when it was just oozing lava. And that's a small enough eruption that if you're dodging bullets, you might not report it. On the other hand, sorry, I have a cat yelling at me. On the other hand, if you have a larger eruption, like a VEI3 or a VEI4 or 5, so St. Helens in 1980 was a VEI5, my apologies for the cat. If you have this larger eruption, then it turns out you make note of it even if even if there's something terrible like a world war going on. So it turns out this really is an observational bias, this increase in activity. So no, they're not increasing. This is good. It's that we see this detection and reporting have improved. All right. Now, to wrap up this first part of the talk, I just want to point out that the Global Volcanism Program maintains the world's most comprehensive record of volcanoes and eruptions, and our website is volcano.si.edu. And we are a trusted source for everyone, essentially, when it comes to learning about volcanoes. And we also have all sorts of other data in there that can be used for any type of project you might have in mind. And other things that even if you're a tourist, you're going to go somewhere, you want to learn something about what's this volcano like, you can use some of our information. All right, so a little bit of if we go by the numbers, right now we can see that there's 46 volcanoes erupting as of yesterday. 79 volcanoes erupted in 2022. And that's interesting because that's the same as the average annual total eruptions from 2010 through 2021. So essentially, in a typical year, about 79 or 80 volcanoes are erupting. And if we look for the previous 10 years or so, if we look from, the total number that are active is like 73 at any given time. So we can see that's pretty much the state of affairs with volcanoes. All right. So now, and I should say, if anyone has any questions, please feel free to interrupt. So now we're going to shift gears and go through a brief summary of the 2018 Kilauea Lower East Drift Zone eruption. So this will be abbreviated through here as the LERZ, because that's a lot easier to spell than Lower East Drift Zone. So this is a picture of Fissure 8, which was, as some of you may know, was the where the majority of the lava came out during this eruption 5 years ago. Right. So for this, So I started to put my own slides together, and then I realized that the smarter way to do this was to use a fantastic resource that USGS developed and present or sort of a piggyback off what they have had, and then hopefully finish with a lot of times you can ask some questions and I can provide additional knowledge that I have. So if you were to go, and I'll put the URL for this at the very end of the talk, if you look up the Kilauea 2018 story map, you can find this website and see all of this great information, which includes videos and other things that we won't have time to go through tonight, but it's a great resource. So if we launch this right here, we can see that, so this is going to be their presentation. And let's see, Cindy, when should I aim to finish so that we have some time for questions?
Let's see, it's 8:40 now. I guess usually we end around 9 and then questions. Does that sound good?
Yep, that should be perfect.
Okay, great.
Okay, thanks. So here we are. We're going to go use their story map, and we'll just start to scroll through here. So I don't want to read everything, but I think as folks probably know or remember, this eruption was a big deal, and we're going to show how it was a big deal in the next few minutes and talk about some of the USGS response to this. So, right, for a reference, we're over here on the right-hand side of North America, and Hawaii is in the center of the Pacific. And if we zoom in on it, we can see that the Big Island is comprised of, or comprises 5 different coalescing volcanoes, and possibly a 6th if you look at Loihi off the south coast. So there's Kilauea, Mauna Loa, Mauna Kea, Hualalai, and then Kohala up here on the north. And these ones that are named right here are all ones that are active or have been active in historic times. So, and in fact, Mauna Loa just erupted and finished erupting in December a few months ago. Right. So if we then look in here, Kilauea on the south flank of the island, its activity is sort of dominated by 3 areas. There's the summit area, and if folks have been to Hawaii, if you had the good fortune to go to Hawaii and you were able to go to the Volcano National Park, you could then see the summit crater and maybe even see the glow of this, or maybe even see active lava lake, depending on what the lava was doing. But there's two other areas where a lot of activities happen: the southwest rift zone and the east rift zone. And this is a geologic map, a fantastic map showing the different flows that have occurred over the last 2 centuries from these different areas. So you can see there's summit activity, and then there's essentially a series of vents that extend down to the southwest, and then another series of vents that have fed all these lava flows that go off to the east side. And the part of activity where the 2018 stuff focused down here and then up here at the summit. Okay. All right, so before the activity ramped up in May of 2018, most activity for the last 35 years had been at Pu'uo'o, which was right here in the middle of the lower east drift, or the middle of the east drift zone, and it has sent all of these flows mostly down to the south. And it had impacts on people on occasion. So the Royal Gardens subdivision, which is here just to the southeast of Pu'uo'o, had been damaged in between 83 and 2011, and there were folks still living there at various times, and then they got forced out because the lava came in and destroyed their homes. There was also some activity that extended lava flows down in 2014 that extended down towards Pahoa and almost clobbered Pahoa, and there was concern that it was going to take out the power plant and some other things that were in this area. There was also, for folks that might remember, there was an exciting thing where one of these flows was going along, spreading slowly, and then it entered a big long crack in the ground that was from a previous just a crack between some lava flows of a previous eruption, and that acted almost like a lava tube and allowed the flow to very rapidly go a long ways quickly without cooling much before it popped out again, and then made this more normal like surface flows. Okay. Now, starting in 2008, the summit area had a very active summit lava lake in the Halema'uma'u crater, and this this, if you read the Smithsonian Global Volcanism Program weekly volcanic activity report from 2008 through about 2018, most of those reports said something like during the last week, the lava lake rose and fell, and then had some other data. But sometimes it rose and fell, and sometimes it fell and rose. But basically, the lava lake was going up and down inside of this vent, and it's a little hard to or it says right here, it started out as 35 meters wide, so 115 feet wide, but over time, this thing broadened quite a bit until ultimately it was about 300 meters across. So 1,000 feet from left to right with the active lava lake in it. And it also, the plumbing here was not a vertical system. It tilted, it sort of went down at a little bit of an angle. So there was one side that was very much overhanging and periodically would fall into the lake, and that would actually generate explosions. So we learned quite a bit about how lava lakes work, or continue to learn about how they worked from that activity that had been happening from 2008 through 2018. Now, I joked that the reports from the weekly volcanic activity report were just the lava lake rose and fell, and that's what pretty much every report was until May 2018, where things started to get a little bit different. And so at this time, we saw there was an overflow of the lava lake, which had happened a few times before. And then we started to see that Pu'uo'o down here in the East Drift Zone was starting to inflate. So, at the same time, it was erupting less. So if you think about this as a linked plumbing system, we have more magma. The magma up here is rising at the overlook vent at Halemaumau. It's pushing up higher and higher. And we see that Pu'uo'o, it's like it's getting plugged up. I mean, it's not quite that simple, but imagine you have a garden hose down here, you're putting your thumb over Pu'uo'o. That's allowing pressure to build, which means that it's starting to inflate down here. And so magma was then accumulating beneath the cone. And we can see that this was starting to cause a little bit of concern. And Pu'uo'o then started to collapse. So it started to fall in on itself as this was happening, and it made these plumes of red ash, as we see in this picture here. So this is essentially, if you look at a cinder cone or a scoria cone where there's all this oxidized lava, that's what this is. So this is oxidized. It's dust kicked up as the red oxidized lava that makes up Pu'uo'o is falling in on itself. The cinders or the spatter that formed it is falling in and breaking apart and then getting kicked out of the dust cloud. All right. Then on May 1st, we saw that the summit lava lake began to deflate. Sorry, the summit began to deflate and the lava lake started to drain out. And this then raised the question of where's the lava going? And I encourage you on your own. I'll take the link at the end of this and you can go and watch the video showing where these earthquakes are happening, because the seismicity started to say that things started to kick off down to the east into the lower East Drift Zone. And at the same time, on May 2nd, the ground started to crack in the Leilani Estate. So this is a subdivision down here. So Pu'uo'o is right here and Leilani Estates is right here. So this is quite a ways away from where active eruptions had been happening, and ground cracks started to appear. And a ground crack is exactly what it sounds like. Here's a person standing next to some cracks that have opened up in the ground. And if you remember your structural geology, these look like really nice en echelon cracks. So this is like a combination of extension. So the right side is moving away from the left side, and also a little bit of lateral motion here. And steam started to come out of these. So that seems like a scary. If that seems like a scary thing, it should be seem like a scary thing. You don't want cracks to be opening up that then have steam coming out of them. And then on May 3rd, the very first fissure opened. And this is a picture. There's a map where we can see it in the subdivision. The white lines are the roads. And I should clarify, the picture here on the left, the map view, is showing the Hawaii after the eruption has stopped. So when this began on May 3rd, lava flows were not where they're shown in this picture. Instead, this would have been, our satellite image would have been green with little white pips for the houses that were there. So May 3 at 5 p.m., fissure 1 opens up and you can see it right here. here's the lava that is a new vent is formed, and here's some houses just a couple 100 meters away, or not even 100 meters away. And this now the alert level is raised, and so this made for a change in the response. So at this point, as of let's see, the next day, 5 more fissures opened up. So we can see now the fissure 1 was right in here, and I don't remember the order number, but they're ultimately in this picture. There's 5 fissures that are extending in essentially a nice east-northeast line, a little bit of on echelon behavior there, and most of these did not make big eruptions. So as it says here, they were short-lived and erupted pretty viscous lava. You can see in this picture here, it's making a flow that's probably 10 or 20 feet thick. And that's right at the vent right there. That's why it's throwing up lava into the air. The next day, or sorry, the next week, an additional 9 fissures opened up. And again, these mostly fed, these were spatter that was feeding flows that didn't travel very far or very fast. And so you can see a picture right here. I mean, that on one hand, that's a terrifying wall of lava coming at you, but it's also, this is not moving super fast. This is the kind of thing that you truly could walk away from. Now, if we look at what was going on up at the summit, we can see that the lava lake had kept draining over this time. And this is a great picture here showing that although we think of Hawaii as erupting fluid lava all the time, that's not always the case. In fact, Kilauea has made some pretty big explosive eruptions. One of them even happened 99 years ago, where this is a great big column of ash coming out of the Halemaumau crater, and this eruption even killed someone. So it can and has erupted explosively, and this made for some concern for the hazards community. And let's look back at this for a moment. If you may or may not remember, but air traffic was diverted and closed for a little while on the Big Island because of the ash. As you probably know, volcanic ash tends to shoot down airplanes, and so for good reason, air traffic controllers and airlines like to keep aircraft away from volcanic ash. Now, at this point, the park closed as of May 11th, and there was a little bit of a pause in activity for, I guess, about a day and a half, and then the next eruption began. And now this is an interesting one. So I'm going to put this as a question to everyone in the audience here. What composition of magma erupts at Hawaii? Someone unmute and say.
Basalt.
That's right. Hawaii erupts basalt, and yet here we are. That's exactly right. I mean, you could get frisky and say that it erupts a pickrite or something, but that's just a basalt with lots of olivine. Hawaii erupts basalt. That's what it does. And then on May 12th, fissure 17 opened up, and fissure 17 was erupting andesite. That's weird. Now, if it's weird, but it's also one that we can explain if we think about the system of Hawaii. We can think that we can realize that, well, fractional crystallization, if you take basalt and let it crystallize for a while, you can, and you remove those crystals, the remaining residual liquid, the remaining magma that's there will be andesitic in composition because you're preferentially crystallizing things like olivine and pyroxenes. And so that's what had happened here. The magma that erupted from fissure 17 was a blob of old magma that had probably been sitting there for about 30 to 50 years, and it had cooled and crystallized enough that it had evolved into an andesite. And it was tripped, or it was triggered by this ongoing eruption, by the fissure that was, or the diking that was happening underneath, nicked this and caused this blob of magma to erupt at fissure 17. All right. Now, as I mentioned a moment ago, this caused the explosions caused an increase in the aviation color code, and so basically aviation was shut off for a while. And this was also the moment in May 16th or May 17th that USGS relocated their observatory. So if anyone had visited Kilauea back in, well, more than 5 years ago, and you went up to the Jaeger Museum up here at the summit, one part of the building is the Jagger Museum. The other part was the Hawaii Volcanoes Observatory, which is was a beautiful place overlooking the crater and the volcano. An absolutely wonderful place, and in retrospect, probably a terrible place to site a volcano observatory where it's right next to the volcano that it's observing. So sure enough, the decision was made to evacuate because there was, you don't want to have your observatory with critical infrastructure and critical people, well, any people being right next to big exploding eruptions. All right. All right, so if we move back south or back to the east onto the Lower East Rift Zone, we can see that these lava flows continue to erupt. So what had started as a little thing in the Leilani Estates had now progressed further to the east-northeast, and it sent some flows quite a ways now. And some of these were starting to also be much more fluid. So these were no longer blocky, sluggish flows, but instead pahoi flows. We were able to move quickly. And we can even watch one of these here for a moment. You can see, if this will work, how quickly these flows are going. That was not what I thought it was going to show us. But we can see that these are sending big, long rivers of lava that are extending for many kilometers right here. And at this point, they started to have ocean entries. So lava started to enter the sea, and this created another type of hazard called lays, which is lava haze. And this is, as it says here, this is a particularly nasty thing because it's fine ash that you don't want to be breathing in. You really shouldn't be breathing in glass, especially when it's transported with hydrochloric acid. And so this was an extra hazard that was developing, and also one that was causing it made observation and gave civil defense a bit of a headache because you had to keep people away from the water. People want to come and watch and photograph the lava entering the sea, and clearly that's not a good idea. All right. A new pit crater opened up at the summit, and we're going to see some really interesting, you can watch some interesting videos of this at some point if you want, showing the summit collapsing. And meanwhile, fissure 8, which is right along in here, reactivated, and this now becomes the dominant fissure for the rest of the eruption. We're going to step out of the website here for a moment and look at some things. So I mentioned a couple minutes ago that the map we're looking at is showing this lava right here is all stuff that came about during this eruption, or just about all of it is. You can see there's a red lava flow sitting here on top of these white roads showing the Kapoho Bay. And these roads here ended right there because the bay used to sit right there. And so if I'm clever and I can step out of my presentation, Kapoho Bay, those roads we were looking at a moment ago, end right on the edge of this bay. And this was a beautiful place. It had there were several hundred homes around in here, and a lovely bay that people they lived around. It was a great spot. There was also a lake over here inside of this old cinder cone. So this was Green Lake because it was a green lake. And if we look back at this lava flow comes in and it starts to enter and destroy the community of Kapoho Bay. It also sent a finger of lava into Green Lake, and within about, I think it was 12 hours or 8 hours or something, the lava hit the water and evaporated all the water and filled in the cinder cone. So where there used to be a lake inside the cinder cone, now there's just more of the lava from fissure 8. Okay, so the other thing that was happening right now was up at the summit, and this is we're going to look at this for the last couple slides here in a moment, and we'll be able to see that the summit crater, this is a view looking at the Halemaumau crater, and it had this great big, this is what it looked like before the eruption, and then over the course of the eruption, the whole floor just fell in and fell in a long ways. This does show this is a time lapse. We're looking across more or less the field of view on the left there, and you can see the floor is falling away in this in the crater. And here's the timestamp up on the upper left, June 30th, July 1st, July 2. The floor just falls away in the crater. And we're going to look at this as we step out for the last couple slides here. So at the end of this eruption right here, we can see that the lava flow had come in and had totally inundated Kapoho Bay. What used to be a bay is now, if anything, it's a peninsula. Several hundred homes were destroyed. There were no fatalities. All the people were able to get out, but their community was destroyed. All of their possessions or their houses are gone. Their lives have been upended in a huge way. So one thing, the other part of the human thing, then we'll look at the last couple science slides and have some questions, is this was a huge USGS response. So as the text says here, for over 3 months, there were the almost 30 full-time staff members of Hawaii Volcano Observatory, but then more than 90 other USGS and other scientists rotated through, and it was a huge, it was an enormous effort on their part, trying to keep track of this, trying to maintain watches, trying to essentially they develop an incident command structure, which is something that like the wildland fire community does, or disaster. There'll be an incident command structure when there's a hurricane. It's a big setup, and they were pushed to the limit to try and respond to this, and they were able to do it. But if it had kept going for a while, I don't know how they would have, if they would have been able to maintain it, because it was a huge burden on all of those staff. So for the last couple slides here, I wanted to mention something about the summit deflation, because this is an interesting one. So the summit was deflating, and then we start to see, starting in mid-May, there were these series of explosions. And if we look at this, they follow this almost quasi-regular or periodic sequence. And this right here is from July. And I can remember sitting in the conference room at Natural History Museum, and we were looking at the real-time data that USGS was showing on their public website. And you could look at this, and after a little while, you can see that it looks like these are happening about every 12 hours. And so you could say, well, the last one happened 10 hours ago. I'm pretty sure we're going to have something in 2 hours. And by and large, you'd be correct. And so each one of these explosions was accompanied by, or these explosions and deflation events was accompanied by about a magnitude 5 earthquake that was happening up in the summit region. So the folks living in the town of Volcano up near the summit were getting shaken twice a day for several months by magnitude 5 earthquakes. The USGS staff who were stationed up there in sort of a temporary observation post one of them described it today to me as, she said it was like being in The Shining. You're in this creepy building and it's shaking and bad stuff seems like it's going to happen at any moment. All right, so, and then here's a couple pictures just showing that before and after of the summit. So beforehand, it's a big hole in the ground, but it has a nice flat bottom. And then after the eruption, we can see that it's gone really deep. And here is, for a sense of scale, you can see that it dropped about, what was that, 800 feet or 650 feet or so that it dropped during the collapse, so that we can see right there. All right, so to the last bit is, how big was this eruption? About 1.5 cubic kilometers in 4 months. And for reference, if you took the National Mall and buried it almost 1 mile deep, that's how big it would be. That's how much 1.5 cubic kilometers is. That's comparable to, that's about a third of what erupted from Pu'uo'o, but Pu'uo'o did that over 35 years. And this eruption did over a third of a year. It's similar to what came out from Tomatic or from Bardabunga in the 70s and in the 2015s, but it's about a factor of 10 less than the Laki eruption in Iceland. All right, so to put this up here and finish and open up for questions, please do come and visit our website, volcano.si.edu. And to look at that story map that we were using just now, you could type in Kilauea 2018 story map, or probably just Kilauea story map into your search engine and get it, or you could go to this URL here. And with that, I would welcome any questions that folks have.
Well, thank you so much, Dr. Andrews. That was just fantastic. It's just amazing that what you've done with that, the database, and then to show, but then to also to show that life cycle of the Kilauea eruption in 2018.
Sure.
So there's a question here in the chat. You know, that there's like that, there, it's from Marilyn, and she says, suspect that fracking may contribute to an increase in earthquakes. Is there anything done by humans that may contribute to volcanic activity that they've come across?
Sure, that's a really good question. It turns out for the most part, there's not much that humans do on a small scale that contributes to that could trigger a volcanic eruption. If anyone remembers the original Hawaii 5.0 show, there was one of those from the 1970s. The villain, who was a rogue USGS volcanologist, was going to trigger an eruption with dynamite in the East Rift Zone. That wouldn't work. Now there is humanity, or rather, there are global factors that can make for an increase in eruptions. So as ice sheets melt, or as glaciers melt, especially if that happens very quickly, like if we get rid of all the ice sheets over 100 years, which would be a bad idea, but if we were to do that, we would see an increase in volcanic eruptions, but it wouldn't happen like instantly. It would be something that would happen over hundreds and thousands of years. We would see an increase in activity. So that volcanoes are pretty they're pretty big critters and hard to make them erupt, which is good.
I remember that there was a relationship between earthquakes and volcanoes. That's what they told me about in Guatemala and all that kind of thing. And so this earthquake activity that's happened in Turkey just recently, is that associated with any kind of rift zone or earthquake activity? Or is that non-volcanic?
Or it's those ones are non-volcanic. I need to look at the exact fault system, how that goes, but I think that's more of it's like a large strike slip or transpressional system, which is sort of like roughly analogous to the San Andreas system in California, where you have two plates moving past each other like this, rather than a subduction system where they'd be one's diving down. And then the subduction zones typically are the ones that have volcanoes nearby. Now you can get volcanic unrest can sometimes be triggered by earthquakes even a long ways away. So the 2003 Denali earthquake in Alaska, which was a magnitude 7.9, the way that the waves, I guess it'd be the P waves from that earthquake propagated to the southeast, actually triggered some increased rumbling at Yellowstone. It did not trigger an eruption because Yellowstone did not erupt in 2003, but it did make for some unrest that happened there and some little bit of changes that happened.
Interesting.
Okay. You were talking about hydrochloric acid in the gas. Is that as a result of breaking the salt in the water when it
Yes,
goes?
that's right. It's the HCl
That's what's generating the chlorine.
Yeah, that's right. So it's the hot magma or the hot lava entering the sea is reacting with the salt water and that's what's making the hydrochloric acid. And of course, and you're sort of getting like three hazards in one. You really don't want to breathe in hot steam. You really don't want to breathe in volcanic ash. I mean, that's just fine-grained glass, so you should do that. And you also shouldn't breathe in hydrochloric acid. So having three nasty things in one is what the laze is, the lava haze.
Does the heat break the water molecule up? And
I
then
think that's right. I think it's
it
because it's
also
very,
breaks
very
the
hot.
bond
Yeah.
between the sodium and the chlorine, and then the
Mhm.
hydrogen and the chlorine
Yeah.
get together, and you got hydrochloric.
That's right. Let's see. I see Irene has a question in the chat, which is, what does Smithsonian learn from this eruption that may influence response to or the understanding of future eruptions? So that's a really good question to ask. So one of the things that was an outcome of the 2018 eruption was there've been discussions among the USGS and academic and Smithsonian and sort of the worldwide volcano community before 2018 about how do we work better during an eruption, and how do we help. There's some things that we can do that USGS doesn't do so well, and there's some things that USGS does that we don't do so well. So how can we back each other up? And that the 2018 eruption provided a real kick in the pants to try and make us work better together. It's not that we didn't work well in that eruption, it's just that we saw there are so many ways that we could do better. And then the other one, the understanding the future eruptions, I think seeing that periodic behavior of the explosions and the collapse, there's going to be there has been and will continue to be a lot of work done on that particular cycle and some of the other things that were happening there. Yeah. To see, there's a couple other questions in here I want to make sure I see. So I saw Marilyn ask, the question about human contribution to volcanic activity. Oh, Kathy. Yeah.
Hi, Dr. Andrews. I don't know how to type a question. I'm on my cell phone. But I remember the 2018 episode, and my first thought was, how in the world could a builder get permit to build and sell homes on a rift zone? And then I went on Zillow and looked at some of the home pricing, which was dirt cheap. So
yeah,
I don't understand how to get permit to build homes.
so, yeah. So you broke up there a little bit, but if I understand what you're asking, right, it's sort of how does what's the land use zoning look like in Hawaii that allowed them to build there? It's a good, I mean, that's a good and a tricky question as well. I think one of the issues is that there's not a lot of land in Hawaii. It's the big island. I mean, it's the big island, but it's not that big. You have limited space. People want to live there, and they need a place to live. And there's you're right that from a geologic standpoint, a volcano hazard, looking at it with especially with hindsight, we would say you probably shouldn't be building where this rift zone is, where these lavas might go. On the other hand, where those communities are, lava hadn't been through there for several hundred years, probably, maybe longer for some of those spots. And so people might make the very sensible, very understandable approach of, I can buy this land and I can build my house, and this is where I can live, and this will be my home. The volcano is probably not going to erupt and get me. And we see we see similar things with other geologic hazards. So when we see with earthquakes, we see, like, I'm from Portland, Oregon, and if we're really honest, we might say we probably shouldn't be living in these places that are going to get hit by a magnitude 8 earthquake. That's not too smart. On the other hand, it might not happen for another 100 years, so sure, go for it. The same, or folks, yeah, don't go for it. But the same kind of thing with people who are building in like a floodplain. They might say, like, yeah, it's not the smartest place to build. On the other hand, they've got to live somewhere. So fortunately, they don't ask me to design the land use laws.
Back in the far distant past, about 1960 or so, some of our fighter pilots used to fly through volcanic clouds deliberately, because the lower tolerances on the aircraft, they could clean out a nice jet engine by flying through the cloud. Nowadays, of course, you get glass melted on your part, so that doesn't work. But back then it did. It cleaned an engine very nicely.
Huh. That's that's on the one hand really exciting and also kind of terrifying.
Oh, yeah.
Yeah,
Pilots do that.
yeah. Well, it's
Military
also
pilots do that.
it's also one that's jet. So there's two things that when an aircraft goes through volcanic ash, there's two things that can happen, or two things do happen. One, there's the abrasive aspect, like you're flying through a cloud of very fine grained sand. So you're essentially sandblasting your aircraft, which is probably not a good plan. The other thing that happens, like Quentin just said, is the jet turbine is hot enough that it will melt some of that material. And so you suddenly, instead of having this perfect precision GE or Pratt & Whitney, whoever made your jet turbine blades that are all perfect shape, suddenly they're not perfect shape because they have melted goo all over them. And the fuel nozzles might have goo on glass, molten glass covering them. So then things tend to go bad when modern jet engines enter ash. A
You
piston
don't
aircraft,
glaze up, you glass
yeah.
up.
That's right. You glass up or you melt up. A piston aircraft, like an old propeller plane, it would have other issues in there, but it would not have that melting problem. It would mainly have the abrasive problem. Let's see. So let's see. Jeff has a question about, I understand groundwater has some effect on volcanoes, especially on the composition and fluidity of the lava. Have there been known cases where human modification of groundwater have affected a volcano? To the best of my knowledge, I don't think so. I could imagine where it may have, or where it could, but typically where groundwater can affect eruption style is if rising magma intersects groundwater, it can flash that water to steam and make a phreatic explosion, so a big steam explosion, which is a bad thing. Or if it mixes with the water, it can make what's called a phreatomagmatic explosion that's potentially even more powerful. But normally those the heat of the volcano tends to drive most of the water away from it, and so you'd have to have groundwater pumping that have been happening right where the volcano happened to be going up.
I'm back.
So, yep. Let's see. I think there's a question for Irene in the chat.
And then there's Mike said, let's see, where
it's
should
not
we
this
go?
one, so let's start it at 7.
He said, where should we go online to understand the Turkey-Syrian earthquake info? So is that USGS? I think they have some kind of earthquake thing, don't they?
Yes, I would use the USGS earthquake portal, or if you did USGS earthquake Turkey, that should pull up their resources, I think.
Okay, great, thank you.
Yeah.
Oh, that's great. And so the eruption that just happened in December or whatever, this was not the same area. It was a different.
That's right. Yeah. So the eruption, there was an eruption of Mauna Loa that started in
Mauna Loa,
and it started at the very end of November or the start of December. I should remember this, and it lasted for about a week and a half or 10 days, excuse me. And it happened from up near the summit of Mauna Loa. So Mauna Loa is the biggest mountain in the world. If you measure Hawaii from the seafloor up to the summit, then Mauna Loa is really, really big. It's substantially bigger than Everest. As it is, it's a mere 14,000 feet above sea level. So it's still a big mountain. And it had an eruption that generated these flows that went from the summit region down maybe 6 or 8 kilometers to the east or to the northeast of the summit area over the space of about a week. And was fortunately, there was no one in the path of those. There was no damage to infrastructure or anything like that. Instead, if we think about there being like a perfect eruption in the sense that no one's in danger, no buildings were destroyed, no infrastructure was hurt, then that was a pretty good eruption.
And so I guess the stuff that you developed in the 2018 monitoring of and response to that earthquake, you were able to do with this 2022 eruption as well.
That's right. So USGS had a lot of lessons that they'd learned from 2018, and also a lot of new technologies that were developed and field tested in a big way in 2018. So UAVs, so unmanned aerial vehicles, and instrumentation like that, they were flying those and able to get those out, I think, for this eruption. The challenge with the eruption at Mauna Loa in December was that it's pretty high up on the mountain and was challenging to get up to. So the Lower East Drift Zone eruption, they could drive to not very far from it, or do helicopter flights at low elevations, whereas taking a helicopter up to the top of Mauna Loa is a big ask for a helicopter.
Wow. Oh, goodness. So let's see.
Thank you. That's really excellent presentation. But I've seen some of your earlier presentations you've made in interviews, and I know this wouldn't be complete unless you got the standard questions of, given the bias that there is in terms of observation, are the volcanoes increasing? Number increasing, decreasing, staying the same, and also the question about Yellowstone.
So we're holding steady with our eruptions, a number of eruptions, and in fact, every year or so we probably strike a few volcanoes from the roster. So the number of active volcanoes, Holocene active volcanoes, is decreasing with time, and that's because we know that things that we used to think are volcanoes are not, or things that looked young. Someone goes out and dates the eruption, and if it's an eruption deposit in the Altiplano of Chile where it never rains, you could have a 30,000-year-old eruption deposit that looks like it happened last week. And so until someone goes out and dates it, we don't know how old it is. Yeah, so Yellowstone, I was joking that I'm going to send all questions about Yellowstone to the USGS scientist in charge for that, because he gets those questions constantly. But the view that I have is Yellowstone will erupt again sometime, but almost certainly not in our lifetimes. And it's also a very, very well monitored volcano. There's a lot of instrumentation there. You can log into you can go in and look at the real-time seismic data coming out from Yellowstone and see that you can see that the wind is blowing for the most part, because the wind sometimes is strong enough to shake the seismometer. So I think that Yellowstone will erupt again at some point in the future. There's a lot of things I worry about rather than Yellowstone. And the other one is, when it does erupt, it's almost certainly not going to be the big one, the thing that happened 640,000 years ago. It won't be that big of an eruption. Instead, it would most likely be a much, much smaller eruption.
Thank you.
Yeah.
Well, thank you so much, Ben, and I just appreciate it. Are there any more questions? All right.
I was wondering, how far was this from the national park? Because we were out there in 2005 and we saw a lot of things you spoke about.
Yeah. I think that the eruption, so the summit activity, of course, was happening right in the middle of the park in 2018. And then the other activity was happening just a bit outside of the park. Certainly when it was happening in those, actually almost all of it was happening outside of the park, because it was happening in Leilani Estates and other subdivisions, which are very much not in the national park. So it's still, it made for, when you're doing geologic work in the national park, that has its own set of permitting requirements and other aspects. In this instance here, the permitting and other aspects involved with the trying to do geologic work in the eruption, it became, again, it's very much like when a big forest fire happens in the West. An incident command structure gets put in place, and it is a tight, controlled space. They had roadblocks set up. No one goes in without a permission slip signed by signed by someone much higher up in the food chain, and that's to keep everyone safe, and it worked. I mean, only a few people were injured in this eruption, and it wasn't like they were injured because they got caught by surprise from a lava flow cutting them off or something. So.
Okay.
All right, well, thank you very much. And it
Thank
was
you.
wonderful, wonderful presentation. And
Thanks.
thank you so much.
Absolutely.
right.
And and
Thank you, Ben.
I put the link to that USGS resource in the chat, and I can also send it to, I can email it to Cindy as well if anyone wants that link to the USGS page.
Oh,
Very good.
great.
Yeah.
Fantastic.
Sure.
I see it here in the chat too. Yep. Thank you very much.
Of course.
Yeah. Be fun to go look at your website too. That the database, that looks fantastic.
Yeah. Thank you.
All right. Andy says, come back and talk to us about anything, anytime.
Sure.
Yeah, for
Thank you
sure.
very much.
Thank you, Ben.
Thank
Thanks.
you.
Thanks,
Well,
man.
with that,
Great
I'm going to
presentation.
for a close to the meeting, and thank you all for coming, and we'll see you next month.
Thanks, Kenny.
Thanks,
Thank
guys.
you. Okay.
Good
Bye.
night.
Thank you.
Thank you.
Bye.
Bye-bye.